Okay. And we also, so this is when we do it term by term, taking the derivative, and we already have that these here have the same radius of convergence. Okay. And so now we have the following theorem. That if you take a power series, so you take a power series like this, R is the radius of convergence. And if L here is strictly less, is some positive number, but strictly less than the radius of convergence, then these guys here converge to right. So these, when you're summing, when you take a finite sum, these here converge to this uniformly, but not only these. Uniformly. But not only that, but you also have that, more interestingly, you have that that this sequence here, k minus m. K factorial divided by k minus m factorial a k x k minus m. That these sequences here converge uniformly to the derivative. This is f of x to the m derivative of x of f. So we have these functions, but that we already proved that these functions here converge, and their derivative here converge uniformly, like this. On the same interval. Okay. Now, why is this the case? So this here is, again, it's following, so this follows to prove, follows from the same theorem, follows from the theorem we proved earlier, we showed earlier. And let's just go through that. So let me go through it. So let's assume first that m is equal to 1. Right, so I just take one derivative. Right. Well, then I'm looking at this sequence here. Sorry, k xk k equals 0 to n. I'm looking at these that converge to this infinite, they converge to f. Right, f again is this infinite power series. And I'm looking at the derivative of these guys, so these are these. And I know now that these here converge uniformly, and these here converge uniformly to the power series, that is this infinite series. Right, this here was the finite part of it, and this here is like the infinite part, the whole thing. Right, so we have that. this means in particular that, so this thing here implies, of course, that that when you're looking at zero, when you're looking at zero, right? So if you evaluate this thing here at zero, then in this one here you get in this is the sequence of functions, fn of x from before. These are the fn prime of x. Right, and so now I claim that, so the theorem that we proved earlier is that if you take a sequence of functions that are differentiable and their derivative is continuous, these are all polynomials, so this is definitely the case. And we know that these values here, fn, in fact, at zero, they're equal to f of zero, right? So this is like, so we had three conditions. We had that the fn in some particular point that we call x0, this is now 0, that this converge. We have that the f prime was converging uniformly. Well, we know that these here converge uniformly. And then we had that the f prime should be continuous, but they were obviously continuous. They were polynomials, right? Then we had that the derivative converge uniformly, and that the function that they converge to, the derivative converge, and also the original function converge, right? And that the derivative converge uniformly to the derivative of the function that they converge to. Right? So you see that this is just checking that we have the tree property from the theorem before, and then we get the two conclusions. And the one conclusion that we're interested in is that this here is then the power series for the derivative of f. Okay? Now, okay, so now, and then you can do the same thing with, so let me just say that, you can do the same thing if you take, if you are integrating. So here we proved, so suppose you take a sequence here that is converging to f. Well, suppose you take a power series here, sorry. Suppose you take this power series, k, xk, k equal to 0. So this is the finite, this is the power series, sorry. And suppose I'm interested in what is the integral from a to b of this power series, f of x dx, right? And here I'm assuming that a and b are in the integral where the power series is converging. So you have this, right? So this means, of course, that if you think about it, that you have here 0, you have r, you have here minus r, and then a and b is lying. And so this means that this whole interval is lying comfortably inside some interval like this. Right? Okay, and I'm asking, what is a nice formula for this integral here? And so then, well, I can use not the theorem we proved earlier, but the theorem we proved last time. And so what is that? So if I define fn of x to be equal to the sum here from k equals to 0 to n of ak, xk, sorry, x to the power k. These here converge uniformly to f of x on any interval like this when L here is strictly less than the radius of convergence, right? So they converge here uniformly. But the theorem we proved earlier was that if you take a uniform convergence like this, and you take A and B in this interval, then the integral of these guys here converge to the integral like this, right? We have this convergence here. But these here are easy to integrate, right? These guys, but because they're polynomial. So they're polynomial, so this means that the fn's of S, when you integrate this from A to B, ds, these guys are the sum here of A, K, sorry, S, K, K equal to 0 to N, and then the integral here, ds, from A to B. Fine? Because it's just that polynomial. And so for polynomial, well, we can just use that it's a sum of these guys, AK, SK, ds, K equals to 0 to N, right? And this thing here, when we integrate that, that's just the, I mean, now it doesn't get much nicer unless you make one of them equal to 0. So you have this. So let me say that if A here was equal to 0 and B was equal to X, so if that's the case, and you're looking at this integral from 0 to X of Fn S ds, we know that this here converges to the integral, right, of the power series. On the other hand, this integral here, right, you know, if, on the other hand, this integral here, if you're looking at the sum here, and then the sum, and now the A is 0, B is X, so then it's this here, AK, XK. Now when we integrate this term here, we're getting, right, so we're getting the sum here, K equal to 0 to N, and then this here becomes A, K plus 1, X to the power K plus 1, right? And so you see that if you're looking at, so you see that these guys here now converge to the integral from 0 to X of f of S ds. Right? That's what we get from the theorem. So the conclusion here is that if you take a power series and you're looking inside the radius of convergence, then the power series is differentiable as many times as you want. And the derivative is given by power series, and it's just the derivative of the term, individual term by term. Right? And likewise, if you want to integrate a power series, then the integral, at least when you're integrating, because otherwise the formula is not quite as nice, but you get but you do get a formula, but it doesn't look so nice. But the integral of a power series, you can just integrate it term by term. Right? Okay, so now the next thing we want to talk about, and that's I'm just trying to set up for next for the next lecture. And so this is, we want to talk about differential equations and how we're using some of the stuff that we've proven in this class to solve differential equation. And and it's like an example where it may not be very obvious that you could use metric spaces to solve a differential equation. but this is nevertheless the case. So we're looking at it. So a differential equation So a differential equation is an equation in an unknown function and its derivative. So let me give you some examples of this. That you take, you're looking at a function f. You're trying to find a function f so this is like the first example. You're looking for a function f so that the derivative is x. Right? Well, we already know that this here, the solutions to this are f of x equal to 1/2 x squared plus some constant. Right? The constant, whatever the constant, when you take derivative, you get 0, and the derivative of this thing here gives you x. Right? And those are the only solutions. Another example here is where you're taking something that looks like f prime minus f squared, so f of x like this. And if you're looking at the function here, f of x equal to 1 minus 1 over x, if you take this function here, and now you take the derivative, so now I'm using the chain rule, so I get 1 minus 1 like this squared, and then I take the derivative of this, so that's minus x. Minus 1, sorry, minus 1. So that's minus 1 times minus 1. So this here is minus 1 minus x squared. And so you see that when you take this function here with a minus sign, right. So when you take, I think it should be a plus, right? So when you take, no, it should be minus. No, that's right. Sorry. Yeah, thanks. I did this one wrong. This here should have been a minus, like that, right? And so this here is now is indeed plus, and then it's this equation. Okay. The next example, so again, a differential equation is something that involved a unknown function and its derivative. So suppose you take something that looks like f prime, f double prime equal to 0. If you're taking the function f equal to some constant, this is a solution. And if you're taking f equal to, say, x, or some constant times x, this is also a solution. They're both solutions. And this is just because the second, in this case, the second derivative is 0. Okay, so now what we will be interested in is we're going to be interested in what's called an ordinary differential equation. And we only looked at this. We only looked at function of just one variable. So this is what the ordinary refer to. So we want to look at ordinary differential equation. And an ordinary differential equation is abbreviated by ODE. And this is, and if it's not an ordinary, then it's usually a partial differential equation, which involve a function that is of more than one variable. So it will involve what's called the partial derivative of the functions. Okay, and the unknown function will be denoted by y. And the equation that we're looking at is that we want some particular value at, say, 0. And then we want that the derivative is satisfying an equation. And the equation that we're looking for is that we have f here and g are given. So think about those as functions that are given. Those are two given functions, but you know they may not be super nice. But you know that f is differentiable, and the derivative is continuous, and g here is continuous. But in principle, you know they're given. And now you're looking for, but it may be very, very complicated. Maybe f is sine, or you know something like that. And so you're looking for a unknown function y, so that the derivative, so y, you think about y as a function of x, and the derivative of y is supposed to be equal to f, but is now applied to this unknown function, and then plus g of x, right? So this here is much more tame, but this is a bit complicated because it involved the unknown function, okay? And so we want to see, so we are asking, so question, does this equation, does this ODE have a solution? And if is the solution unique? Right, so by this we mean, right, so we're looking for a function. So here's what we're looking for. We're looking for a function y defined on some interval into R. This function has to be differentiable, so this has to exist. 0 has to be in that interval, right? Because we want this is a is just a constant, right? And and then we want obviously y to satisfy this equation here. Fine. That's what we're looking for. So this is existence. The thing is that what we will prove is that there exists some interval. So we will prove the following. So we prove the following theorem which has many different names and it is attributed to various people. But it's, I guess, most often, named the Picard-Lindelöf theorem. And so this is that given f and g as above, so f has to be differentiable, and the derivative continuous, g just has to be continuous, then there exists, then for any a, there exists a delta greater than 0, such that, and a solution to this differential equation, this ODE, on the interval from minus delta to delta. So we proved that there exists a solution near the origin. The thing is that a solution may blow up. So it may not exist on a very long interval. It may just exist on a small interval. It's all depending on f and g. But in particular, it will depend on f. Okay, so it, and that, moreover, it is unique. Meaning that if you take another solution defined on the same interval, then it must be that solution. Okay? And so, so now I just have a minute or two, but we'll prove this next time anyway. But I just want to, as a teaser, if you will, I will just say that, so the proof of this, so the proof uses the contracting mapping theorem. Mapping theorem. I'll remind you what that is. Maybe I'll remind you what it is. So we call that the contracting mapping theorem is the following. That suppose you take a metric space, X and D. So D is the metric, X is the space. And suppose you take a map from X to itself. Then X is, so then T, so T has a map from X to itself. T is said to be a contracting map. If there exists some constant, that constant, and that's key, it has to be strictly less than 1. So that if you measure distances between the images, so for any x and y in capital X, this is for all x and y in capital X. If you look at the distance between the images of these 2 points, then it's less or equal to this constant that is strictly less than 1, like this. Okay. So that's a contracting map. And the contracting mapping theorem that we prove, I'll remind you about it again next time, but just the contracting mapping theorem that we proved is that, so we proved the following theorem, which is the contracting mapping theorem, that if X here is Cauchy complete, then and T from X to X is a contracting map, matching map, then T has a unique fixed point. So there's a unique, so there exists a unique one, often write like this. There exists one and only one x, so that f, so that, or x0, so that this map takes x0 to itself. So that's a contracting mapping theorem, okay? And so now, so it seems like that what does ODE has to do with this abstract context of a metric space. So it's tied together using this. And then the space X, it's not, you may think that you may think that that's close, but it's not quite the case. You may think that it's like a continuous function on an interval like this. That's close. This here is, you may think that because that's a space we've talked about a lot, this here with this metric D, we talked about with this maximum distance. It's not actually quite the case. It's a little bit more complicated than this. But X is related to this because X here will be a ball around the function that is constant, A in this space. And we have to choose this R carefully, okay? And so that's the space X, and now I haven't defined the map T, but we'll do that next time. And I will remind you about this also. Any questions?